Today we'll be talking about BGP routing. My name is Paco, and with me I have Max.
Right.
So, a brief overview. We saw how we route packets using the shortest route, whether it be Dijkstra or distance vector, but there are also other considerations when routing, such as cost or traffic. So, BGP actually allows us to advertise other attributes in our routes, such as local preference or MED. We These are ranked in terms of priority, and they also are controlled by uh, um, different routers. So for example, a local router or a neighboring router. And we'll go over some of these and how we can use them to control how our traffic is routed. So in terms of controlling traffic, there are three main ways we can do that. The first thing is setting a preference. So we'll change our attributes in the advertisement. So we can set local pref to 69, or we can raise it or lower it. We can also filter, so we can ignore routes with certain attributes. So for example, local pref larger than 69. We can also tag routes with strings, basically. These are known as community attributes, and we can label the routes with IDs. I'm gonna call these community attributes tags from now on. So isn't the shortest path good enough? So why do we want to change the routing of packets? So one of the reasons is business. First thing, we want to avoid routing traffic through our competitors because that costs us money. Usually, in most cases, we want to set the local pref, which is the highest ranking preference, to favor our customers because those are revenue generating. We will set something lower for our own routes, um, and an even lower number for expensive links. And we will put backup links at the lowest preference because those are the most expensive to operate. We also don't want to forward anything between neighboring AESs, especially if they're competitors, because usually this kind of traffic is not revenue generating. So one way we can do that is when we receive a route from our neighboring AS, we will append a tag to it. And at the edge of our AS, the router will filter out uh, any routes with the competitor tag on it so that any other neighboring ASs will not see this path through us. So in this case, C2 will never send anything through us to C1 because it doesn't know of the route because we filtered it out. There are also some traffic considerations. So in class, we saw hot potato routing where we want to exit our own AS as soon as possible. We can also control our outbound traffic. So first, we can set local pref to achieve our desired ratio between links. For example, the second link here is much wider, so we want to allocate more traffic to it because a saturated link causes queuing delays and other problems. So if we set a higher local pref for the second link, more traffic will go down this route. So ISPs have to set attributes and set filtering prefixes carefully to ensure balance. Setting the prefixes in the right way is difficult, and we mostly use regex for that. It is often done manually and is subject to human failure. It's not done in real time. Its outcome is hard to predict, but there are simulators available to see the effect on traffic. In terms of inbound traffic, we have to deal with peers that are unaware of our goals, topology, or load. So it is difficult to allow remote ISPs to influence routing to and within our own AS. Because remote ISPs have conflicting goals, they want to ignore our preferences. And sometimes this even requires external incentives for them to respect our preferences. So one way we can control inbound traffic is setting the MED value. So for example, here, route A1 and A2. Once again, we have a much more wider link for A2. And for example, if router A1 is scheduled for maintenance, we want to pass more traffic through to A2. through this A2 route. So if we set the MED for our advertised routes, then our neighbors, if they see that, they can forward more traffic down the route with a higher MED. However, this requires our neighbors to respect the MED value, which not always is not always respected. So if we want to get our neighbors to choose certain routes, if they do not respect the MED, we can manipulate our advertisements by appending dummies in between the routes, so the path length appears longer. In that case, this route will be a less preferred one over a shorter route. So when we advertise both of these routes, our neighboring ASs will select routes that we want, the ones without extra dummies in them. We can also remotely control routers because recall that changing attributes is a slow and manual process. So we can use a tag, a community attribute, which is mapped to a local preference. So for example, here, router A will have a tag in some of its routes. And when it is advertised to router C, it will see it and set its own policy accordingly. And when router A wants to change something, it will advertise a different tag to its route. And this will once again have a different effect on router C. So comparing both of them, RC is slightly more flexible. We can control our inputs. It also allows filtering and prepending. MED can only change the next hop's information, while RC local pref method can change across multiple hops, but both of them require prior agreement and negotiation. And there's also a risk of misconfiguration with tags. Community attributes can mean very different things in different ISPs. So it's very important that you publish the tag list and you manage your routers carefully, not to propagate these tags beyond where they're needed. Something quickly about smart routing. It's only applicable to small ASs. It is something where we can dynamically change the routes based on the changing traffic. But doing this too often leads to flap damping, which Max will explain later. And this also does not consider the effect on internal traffic.
Okay, so I'm gonna talk about scalability and security here. So first we start scalability. Here we have an issue about memory. So we want to limit the routing table size. And there are two things we're going to talk about. One's going to be protection from others, so it's going to be protecting ourselves, and the other one's going to be protecting other ISPs. So for protecting ourselves, so there's going to be filtering on longer prefixes. If it's too long, that it's too fine-grained, then we're going to drop that advertisement. And also for each neighbor, they have a quota for advertisement. So for example, one can only have a m prefixes, for example. But with a limited routing table, there can be some misses. So we will have a default routing as a fallback. And so the other one's going to be protecting other ISPs. So here's going to be root aggregation. Usually it's going to be done by the tags or community attributes. So this is going to be the bottom left one. So because it's going to be case by case, even though we're adding a new route, let's say R5 here. So because R5 is going to be added and there's no need for new advertisements. And there's going to be, if we add another one, R6, into the network, where R6 is going to talk into our customer D, and customer D can now talk to R5 or R6 to get the service. Now there's an internal advertisement. And if we have if the customer D also subscribe to other ISPs, for example, F here, then we will need to think about like how we do the internal and external advertisements. So that's more complicated. This is going to be the route aggregation. And also the other one we can see on the bottom right, this is going to be another way we can do a route aggregation. Basically just going to be merge for R2 when it's advertising to R1. It's going to merge the prefixes from R3 and R4. Yes, next slide, please. So here's going to be, besides the memory, so we're going to talk about CPU. So it's going to be frequent route updates. And if the CPU is on high load, then it's going to miss some important events. So we want to avoid the CPU to be on to high load often. And so there's going to be flat damping, which is going to be limited propagation of unstable routes. So a route, once this route is stabilized, they shouldn't send updates too frequently. So that's the notion. And that's once um, the route is updating too frequently, for example, then that means we will need to ignore that prefix for a while first. So this is basically going to be on the right-hand side. Then we have this graph. So first of all, we're going to have this prefix being announced. And once we see this the frequency, the update frequency is too high, then we can ignore it for a while. Once the frequency got dropped, then we're gonna use the frequency again. So if we have a lower threshold, and that means we have a much better, much more stable routes, but also we have less options to find the correct path. Next one. All right, so we're going to talk about security. So there's going to be false information to start with. So one thing is going to be import filtering. So we want to send a check this everything that we get to filter out any route update that's about private or special user address update or advertisement that doesn't belong to the customer or other ISP informations, etc. And also we want to ensure the processing directly. For example, we want to remove the MED values from our neighbors when we're actually advertising for other neighbors. And the other one is going to be hide internal resources. So we want to remove the internal routing interfaces. So let others, because they don't need to know those informations. Yes. The other one, the other security issue is going to be denial of service, which is going to be the next slide. All right. So if we see the attack vectors, it's similar as a scalability issue here. But besides the route aggregation, etc., the other mitigation we will introduce here is going to be black hole route. Basically, it's just going to be a route that's going to drop all traffics. Once we identify there's going to be the bot that's attacking our AS or ISPs, so then we can redirect those traffic to the black hole routes. So it's going to protect our services. Yes, that's it.
So we can we can also use some of these techniques that I've mentioned previously to achieve certain effects. So one of the papers we looked at was routing around congestion. So this is a system where it is deployed in a single AS to route traffic around congested or DDoS links. No additional coordination is required beyond the single AS it's installed on, and it is achieved using only some of the techniques we have previously mentioned. So recall that we can add multiple dummies into advertised routes to make undesirable routes longer. So we can use this to manipulate traffic routes. So what this paper does is it reroutes traffic around a congested or DDoS link by appending multiple dummies. And in that case, the traffic will be rerouted around the congested link. So based on that, they created a simulation, and it was found that they were able to successfully reroute around the link based using the technique of adding dummies in these poison routes. And they also found that there was strong performance in that the traffic level was maintained even through a downed or congested link. In this case, strong performance here means the alternate links are uncongested, but we can see for multiple scenarios that we were able to reroute around the congested link. So that's all we have. So thank you for watching.
Thanks.